Hello everyone, welcome to another session on robotics. Previously we talked about how we can quantify a motion of a rigid object in 3D space. And we said there are two types of motions, translation and rotation. Translation can be described using summation of two vectors and rotation using a rotation matrix that's essentially defined using three parameters and three elementary matrices. Now we're going to talk about the rotation matrices in a bit more detail and finally explain how you can use this rotation matrix to describe a general motion of an object in 3D space. We have three elementary rotation matrices for rotation around Z, Y, and X. And any rotation can be described by multiplying these two. It's composed of one, two, or all of the three of these elementary rotation matrices. But how can we combine these? This will give us a bit of insight into combining rotation matrices. Assume you have this object, and at first we want to rotate it around Z-axis. It turns into this, and now we rotate it about the y-axis of the new rotated frame, and we get this final object. Now consider a case where we do the reverse. First we rotate it around the y-axis and then the z-axis of the rotated frame, and we get this object. And as you can see, these two are different, and it gives us an insight into how we can merge two rotation matrices into to give a final rotation matrix. You can see that order of rotation matters. Doing a ZY rotation is different from doing a YZ rotation. Consider another case that first we do a rotation about the Z axis, and then we do rotation about the Y axis of the initial frame, not the rotated frame. We get this. Do it in reverse. First Y and then Z of the initial frame. You get this, and you can see that these are also different. Therefore, not just the order matters, but also which frame matters. Do we use the initial frame as a reference or the new rotated frame as a reference for the second rotation? Based on this, we need some guidelines. We need to have some ground rules on how to define rotation matrices. One of these guidelines is based on Euler angles. This is the most common type of rotation matrix. Euler angles are basically a rotation about Z, Y, Z axis, and all of them are about the already rotated frame. So if rotation, then about the Y axis of the rotated frame, and again the Z axis of rotation frame. The final matrix is the product of three elementary matrices, one Z, one Y, and then another Z. This would give us the final matrix by multiplying the three elementary matrices. If we use this ground rule, then we can always, all of us, develop a rotation matrix that make the same meaning, have the same meaning. And for instance, if you read a paper or an article, usually about modeling of the robots, at first they define what protocol, what guideline they're using. If they say they use Euler angles, you know any rotation matrix in there is composed of three rotations, one around Z, then Y, then Z again. There are other guidelines too. You might say YZ, YZ. Why not ZYX? Why not XYZ? There are other ones as well, like for instance roll pitch yaw. Roll pitch yaw is basically a Z rotation, Y rotation, X rotation, and all of them about the already rotated frame. If you multiply these elementary matrices for Z, Y, X in this exact order, you get these final rotation matrix, and you can see this is different from Euler angles. So if you, for instance, want to model a robot and you say I use roll, pitch, yaw angles, then I know how you have developed rotation matrices. These are guidelines to make sure everybody is using the same notation for building rotation matrices, the same order. And it's important to stick to one guideline. And the one that we use mostly is Euler angle. The roll pitch yaw is more common for drones or mobile robots. Another question that comes in mind is, okay, we build the rotation matrix knowing the rotation angles, but how can we do the reverse? How can you find the rotation angles if you have the rotation matrix? This is how we do it. First, we got to know what is the guideline for developing that rotation matrix. If this is all Euler angles, then we know it's a ZYZ, or it could be roll pitch yaw, or something else. These are the most common ones. If it's ZYZ, then we can calculate the three rotations about Z, Y, and Z using these equation. For instance, the rotation around Z axis is arctan 2 of this element and this element. The same, we can calculate rotations about Y and Z. But how these equations are derived? It's easy. If you look at the rotation matrix for Euler angles, ZYZ, it looks like this, where C shows cosine and S shows sine of an angle. Imagine you want to calculate phi, the first rotation about Z. How will you get that from this matrix? If you look at these two elements, the third element of first row and third element of the second row. Can we get phi from these two? Yes, if we divide them, if we divide R23 by R13, what will we get? We will get sine of phi divided by cosine of phi, which is tangent of phi. Now to get phi, all we have to do is take arctangent of R23 and R13. That's how we get phi. Mostly in robotics, we use a function called arctan2. What does it mean? When you calculate the arctangent of a function, it could give you two different angles for certain specific values. For instance, look at this graph. Assume we have this angle, call it theta. And this has a value of, let's say, 0.5, 0.2. What is theta? Theta would be arctangent of 0.2 divided by 0.5, right? Now consider this angle. Let's call it theta 2. What is theta 2? Theta 2 is arctangent of minus 2 divided by minus 5, which is essentially the same. So if you take arctangent of a value, it could give you two angles for the same value. To avoid this, we use arctan2 function. Arctan2 basically looks at the sign of the values, and based on it, it decides in which quadrant the angle falls. Lots of software platforms such as MATLAB or even NumPy in Python have arctan2 function. So instead of arctan, we use arctan2 to get one definite angle based on the sign of the R13 and R23. Now, how can we get new rotation around y. Let's try to calculate that. How can we calculate rotation around y? We prefer to work with 8 and 2 for the reasons that I explained. For instance, if you look at this element, you can take the uh, arc cosine to find nu. But the problem is arc cosine will give you two values for two angles for a specific value. So it's not good to use arc cosine or arc sine or even arc tangent. We prefer to use arc tan 2. If you want to take arc tan to look at these two first. Let's call this R13, R23, and this would be R33. If I take the square root of R13 squared plus R23 squared, what would I get? I would get sine of nu squared times cosine of phi squared plus sine of phi squared. This is equal to 1, so I would get sine of nu. So the square root of R13 squared and R23 squared will give me sine of nu. We have cosine of nu from R33, so simply we can find nu using arc tan 2 of this element R13 squared plus R23 squared and R33. Then we find nu. Similarly, you can get psi. Think about how. You probably have to use these two. And these are how these equations are derived. Knowing the rotation matrix, we can calculate the angles. Now, if the rotation matrix was developed using the Rolle-Pichia guideline, it would be a bit different because the rotation matrix would be different itself. But if we stick to Euler guidelines, we can always use this equation. One major problem that would rapidly show itself is called the gimbal lock situation. Consider a Euler angles, a z rotation, y rotation, z rotation. The rotation matrix is developed by multiplying the three elementary matrices. For a rotation around z, let's say by alpha, rotation around y by beta, times rotation around z by gamma. These are all our elementary matrices. This is how Euler angle is developed. Consider a case where beta is 0. We don't have rotation around y. What happens? We multiply these matrices and simplify. The final rotation matrix would be this. And now we want to find the angles using this matrix. Use those formulas and Eitan tools to get the angles from this matrix. Can we do it? You can see that now because the middle angle beta was 0, the equations are kind of coupled. Based on this, no matter how hard you try, you cannot find the values of alpha and gamma independently. You can use 8 and 2 for these two elements, but because it would be 0 and 0, it's impossible to get the angle. You can use 8 and 2 on these two components, but it will give you summation of alpha and gamma, not alpha, not gamma. This is a case we called gimbal lock, when the middle angle rotation around y is 0. Gimbal lock can happen for any other types of rotation matrix, not just Euler, even in Rolle-Pichia. Whatever guideline you use, if one of the middle angles is 0, you will have gimbal lock, and it would be impossible for you to estimate the exact angles from rotation matrix. Think about how can you estimate the angles if we have gimbal lock, and consider that we don't usually look at the rotation matrix at one time instant, and we look at it through the time. Think about how you can find these angles, and let's discuss it in the forum and in the class. Last thing I want to talk about is that How can we combine rotation matrix and translation to give a general description of any object in moving 3D in 3D? We're going to use the concept of homogeneous transformation, something you've seen in the vision part. In here, I will give you more details and it will make more sense to you what is a homogeneous matrix. Consider an object, let's call this object P. It's in a point here shown by red. We use a reference frame and a vector to show its position. This is our original reference frame, which is a stationary frame. Let's call it O0. It was initially in O1, then has moved to a point P. What would be the position of the object P in reference frame 0? Using summation of the vectors, we can calculate it, right? So if I call this vector P in frame 0, I call this vector O in frame 0 shows frame O1 with respect to frame 0, and I call this P in frame 1. What would be the position of vector, the point P in our stationary frame? P in 0 is equal to O in 0 plus P in 1, correct? This is wrong. As I said in the previous video, every vector summation should be done in one frame. It should be in our stationary frame. So we have to bring this P1 vector into frame 0. That's where rotation matrices come in handy. So this is wrong. What it should be is actually P0 is equal to O0 plus P in frame 1 times rotation matrix that brings frame 1 to frame 0. Then this would cancel out, everything would be in frame 0. So if we want to define a position of object in a fixed frame and we have only its position in a rotated frame, we have to bring the position into our original fixed frame and then add the distance between the two frames to it. Now, if you remember from the vision part, we said we rather to have all the equation as sort of matrix multiplication. That's where homogeneous transformation shows. Writing the equation like this is really not a good idea, especially if you want to develop algorithms that use vectorial format. Everything should be in matrix multiplication form. That's why we use a homogeneous transformation matrix defined by this. A homogeneous transformation matrix brings one frame, let's say frame 1, into frame 0 and applies displacement as well, and it's written like this. This is a homogeneous transformation. R is a 3 by 3 matrix. Position of the tilted frame is 3 by 1, and then we have 1 0 zeros here. It is a 4 by 4 matrix. Now we can write that equation as P0 is equal to A10 times P1. Similar to matrix, rotation matrix, it can cancel out and brings P to 0. The homogeneous transformation not only rotates it to bring it to our desired frame, but also translates it by vector O10 to show the displacement as well. And that's what we're going to use a lot in robotics. We don't use rotation matrix alone. We use the homogeneous transformation that demonstrates not just the rotation but a translation of an object. So we can use it to explain any type of motion, including combination of rotations and translations. If you expand A1, 0 in this equation, you will see that these two are exactly the same, but this is in matrix format, which would be much useful. So this is how we build homogeneous transformation. Top left is always rotation matrix. Then we have the translation vector, and we append the matrix, but zeros down here and just 1 here. One thing to notice is inverse of homogeneous transformation is not like a rotation matrix, and it's not exactly equal to its transpose. Inverse of rotation matrix is a bit more complicated, and it's given by this equation, and it is never equal to transpose. One thing you can do at home, try to write this inverse for the same plot here. Now assume that you have point P defined in frame 0. How can you write it in frame 1, opposite of the equation I wrote? Then you should be able to find the inverse of homogeneous transformation, which brings frame 0 to 1 now. It should be an equation like this. Try to calculate this matrix at home. Now that we have developed the concept of homogeneous transformation, in the next videos we're going to use this to model the robots, and you can guess how we're going to do that. Basically, the homogeneous transformation shows the position of one point and its orientation in a fixed frame. To apply it to a robot, we will select a frame at each joint and then calculate the homogeneous transformations from each frame to another one. Like the one that brings frame, let's say 0 and 1. And finding the homogeneous transformations for every frame, we can find the position of the robot end effector in our global fixed frame. Simply, if we have sensors here at joints that can measure the position of the end effector in the last frame, let's call this P3, by multiplying P3 with all the homogeneous transformations that we have calculated, we can find the position of end effector with respect to a fixed global frame. This would be a forward kinematics of the robot. Give us the position of the robot end effector in a fixed global frame as a function of all the different types of rotations that any joints can perform. I will expand this topic in the next video lectures, but rotation matrices and homogeneous transformations are topics that are used a lot in computer vision and robotics. Try to go through the examples that I have talked about. Make sure you have a perfect understanding of rotation and transformation, and come to the classes and ask any questions that you have. I'll see you in the next video lecture.